McDuff with us today. Mathematically, I think trained in England, but most of her career, I think, here in the United States. In her English persona, she's a fellow of the Royal Society, and in her US persona, she is a member of the National Academy of Sciences. I believe those are both true statements, right? And there must be very few mathematicians who can say both statements. Are you the only one?
No,
I'm sure we're all sure there are some others, but there are very few. Anyway, it's a great pleasure to welcome Dusa. Embedding ellipsoids symplectically, or something like that.
That's fine. Well, it's a great pleasure to be here. I don't quite know what to say because I'm giving a lecture in a day or two in Rochester. I don't know how many of you are going to this AMS meeting in Rochester. I don't know if I should ignore that and just repeat or say new things. I mean, different things. So a lot of you, you're not going to be in Rochester, so you don't. Okay.
May I make a suggestion? Ignore it.
Ignore. Okay, so I'll ignore it. So I was hoping to tell you about the problem of embedding symplectic ellipsoids and hoping to make it intelligible to people who don't know any symplectic geometry. So for that to be possible, you've got to ask questions if I say things you don't understand. So please ask questions. And really, one of the reasons I like talking about this subject is it's very easy to say what the problem is. I mean, normally these problems are quite difficult to understand. I'm really just talking about Euclidean space, mostly in 4 and 6 and higher dimensions, and with a symplectic structure, and then I'm talking about ellipsoids in that Euclidean space. So let me begin by saying what a symplectic structure is. And that's an even-dimensional geometry which arose from physics, because you think of, if you have a particle moving, you've got position coordinates and momentum coordinates, and they're paired. And so you have some two-dimensional invariant that sort of pairs a position and a conjugate momentum. And if you look at it in Euclidean, in R2, it's just an area, dx dy. In R4, it's just a sum of area forms, dx1 wedge dy1 plus dx2 wedge dy2. And in higher dimensions, in 6 dimensions, it's just a sum of 3 of these things, right? I hardly need to write it out. So that's what a symplectic structure is. And then the question is, what kind of geometry does it have? So it's a question that interests me. If you look at diffeomorphisms of the space that preserve the structure, what can you say about them? And in 2 dimensions, then you're just preserving an area form. So you're just looking at area preserving diffeomorphisms. And if you try and understand what they do topologically, it's very easy. There's a theorem which was definitely proved by Moser, but which must have been known before that, which says that you have 2 regions in the plane, D and D prime, say, and they're both contractible, they're diffeomorphic, so there's a one-to-one smooth transformation between them. Then suppose that the area of D is the same as the area of D prime. Then the claim is that there exists an area preserving diffeomorphism from P from D to D prime. In other words, the Jacobian matrix of this is everywhere identically 1. So it doesn't just preserve the area, the total area, but each little bit goes to something that's the right area. So that's actually a fairly easy theorem to prove. It's not hard. So then you might think, well, what happens in 4 dimensions? Suppose you look in 4 dimensions at something that preserves this, and it's sort of hard to understand what kind of geometric structure is given by this 2 form. What it's doing is making, if you have a little bit of 2-dimensional surface, it'll give you a number. But that it's very inhomogeneous because you can have, if you take R2 with the x1, x2 coordinates, then this form vanishes identically on it, so it gives you no structure. Well, if you take, say, the x1 y1 plane, then it's got full area. So it's not a homogeneous geometry, and it's a different kind of geometry. We're not measuring lengths, we're not measuring angles, we're just measuring these 2-dimensional areas. But it is actually very closely connected to complex geometry. in very interesting ways, which I may have some time to tell you. But anyway, you know, there are a lot of questions that came up about, well, I mean, I'm just telling you a topologist viewpoint. I mean, there's a whole theory of dynamics, of Hamiltonian dynamics, because one of the reasons that people are interested in this structure is that symplectic forms are what give the classical equations of motion. So if you have a function h on Euclidean space, say R4, and you've got an energy surface, h inverse of c, so that's a constant energy surface. Let's suppose c is a regular value, so this is a smooth manifold. So just a smooth three-dimensional piece of space. And then you have what's called the symplectic gradient, which is you take dh, which is a one form, and then you use the symplectic form to get a vector field. So that's omega. This has a property that omega, if you put xh in at the first place, that gives you dh. And what it is, in this particular case, xh is just a 90-degree rotation of the usual gradient. So if you have a function on R4, it's got the usual gradient vector, and then you just rotate it. You think of R4 as being, say, 2 copies of C, and then you just multiply by I, so you rotate by half a term in this coordinate and half a term in that coordinate, I mean by rotating. And so you get this which is orthogonal to the standard gradient. And because the standard gradient, of course, points out orthogonally out of the level surfaces, this is tangent to the level surface. And so you get this vector field on your surface. And the amazing thing is that this vector field, if you integrate it, you make it into a flow, then that flow preserves the symplectic structure. And so the Lie derivative, the derivative in the direction of h of the symplectic form is 0. So this is actually the time flow in classical mechanics. So in classical mechanics, you have a situation where the x-coordinates are position coordinates, the y-coordinates are memento. H would be some energy function like kinetic energy or kinetic plus potential energy. Then you look at the flow, you know, the vector field you get, and that would be the time evolution. So if you had your point, you were there in your state space, and then as time moved, you move along this constant energy surface. So this is energy preserving motion. But you see, that means that symplectic geometry is very closely tied to dynamics. And it gives some invariants. So what's interesting is that this gives topological invariants of symplectic structures. You think that this is very analytical and somehow we wouldn't see it topologically, but you do. So that's what I want to try and tell you a little bit about. Anyway, one of the things is, as an example of this, you see, if we just take h to the most obvious function, so h of a point is just a sum, well, actually, the function I'm going to be interested in are the ones that give the ellipsoid. So I'm going to be interested in x1 squared plus y1 squared over a plus x2 squared plus y2 squared over b, and multiply by pi. So take that as your function. And its level surface is an ellipse, right? If you look at h less than or equal to 1, that's an ellipse, because if a is different, if a is equal to b, then it's a ball, or it's a ball, and if a is less than b, it's some kind of ellipsoid. It's got one axis. And I like these coordinates because this is an area. This is the area of the axis. So these are the areas. A is sort of like lines. And so we have these ellipsoids. And if you look at the flow they generate simple harmonic motion, a simple oscillator, which is rotating with period A and one in this plane and period B in that plane. And actually, perhaps I should just do that calculation for you so that you can see that. I mean, if we do this thing, let's take x1 squared plus x squared plus y squared. in R2. And then d of that is 2x dx plus 2y dy. And then we want to do this funny thing. We want to take the symplectic gradient. Well, the standard gradient, of course, is 2x d dx plus 2y d dy. But then I said we want to rotate it by 90 degrees, apply j to it. And what that does is, it was pointing out what is the choice of sign, but I normally make it, you could make it point in that direction, tangent. So it's going to be a rotation. You see, this is x, this is the gradient. It's going to be 2x dy plus minus 2y dx. And if you want to see that that's the right thing, you take this vector and see what it does when you plug it in the first, evaluate it on dx dy. You see this vector d dy eats up that y direction and you get minus 2x dx. So you get that. So that gives you 2x dx. And if you put this one in, well, I've got my sign on there, minus 2y dy, eating that up, you get 2y dy. So this sum really does correspond to this one form. And so it tells you that a quadratic function generates a rotation. And if you have a quadratic function which has got these different weights on it, then you're rotating in the first variable, in the first two coordinates at a different speed when you're rotating in the second two coordinates. So on the ellipsoid, you have this flow, and well, it's got definitely two periodic orbits. It's got one going around the x1, y1 direction, and it's got another one going around the x2, y2 direction. So those are periodic. And if the ratio of A and B is irrational, those are the only two periodic orbits apart from one. Well, if the ratio of A and B is rational, then all the orbits are closed. But the thing is that this structure you have, this flow you have on the boundary, doesn't really depend on this function. It's an intrinsic geometric thing. Because, you see, if we fix the boundary and we change the function, what happens is we're just changing h by some, h goes to some function of h. And what that does is it doesn't change the direction of dh. That just gets multiplied by a function. So it doesn't change the direction of this vector field. The vector field gets a different length, but its direction is unchanged. So, and in fact, the direction of this vector field on here, the xh, can be described as its unique null direction. It has the property that xh is tangent to this level set. And it's a unique direction such that if you put in xh and you put in any other tangent vector where b is tangent to this level set, this always vanishes. So it's a null direction. Symplectic forms have the property that they, in general, they're non-degenerate. They don't have null direction. So any vector, if it pairs trivially with everything tangent to this, it's got to pair non-trivially with something like that. Anyway, we have, you see, on a surface, you don't really see this in 2 dimensions, but in 4 dimensions, you have these hypersurfaces, so 3-dimensional surfaces, and they have these flows on them, which are characteristic. They're the characteristic flow, and they're symplectic invariants. Now, that immediately tells you that the analog of this thing can't be true. It certainly can't be true that if you take 2 regions in the plane of equal volume, that there's a symplectic transformation from one to the other. I mean, 2 diffeomorphic regions. I should point out what's the relation of this and the volume form. Well, if this is omega, and you take omega wedge omega, then that's obviously 2 dx1 wedge up to d by 2. It's a volume form. So anything that preserves symplectic structure has to preserve the volume. And one of the motivating questions was, what's the relation? I mean, how different is it preserving volume from preserving the symplectic structure? And actually, well, Gromov formulated a lot of questions about that kind of thing, and Arnold as well. Anyway, you see, you could just take, I mean, this is saying that in 2 dimensions, areas well, the topological type of the domain up to diffeomorphism, together with the total area, that's a complete invariant on the symplectic morphism. And you can ask in 4 dimensions, is that the same thing? If you have 2 things in 4 dimensions which are diffeomorphic, and if the total volume is the same, does that imply that there's a symplectic transformation between them? And that you can see is immediately false, because we've got this, if this is a region with smooth boundary, it's got this characteristic flow on it, and that wouldn't be preserved. I mean, this one could be a ball in which all the orbits would be just at the same period, they'd all be closed, and this could be an ellipsoid with the same volume, but which only had 2 closed orbits. So you can definitely see that there's some difference here, and the question is, how big is that difference? Is that just, you could just fudge it a little bit? So the next question, you see, if you can't make these things actually diffeomorphic, you could ask, well, is there, say, an embedding which would take this region into sort of an approximation of that region? So you just had to wiggle it a little bit and you could make it close to it. So that's the kind of question that people were asking in the 80s. And I think there were several attacks on it, but the most attractive version of this result, for me, is the theorem of Gromov's, which I'm sure a lot of you have heard me talk about, which is a non-squeezing theorem, and which says that if you take a ball, if you look at a ball, actually it's valid in any dimension, so you take a ball of size A, so A is here pi r squared, so R is the big R is the radius of this ball, so little r is the radius of the ball, and A is the area, so that's the radius little r. And you have a cylinder, which is a two-disk with, say, area A, so A is again r squared, times Euclidean space, where this is a symplectic splitting, so this is, say, the x1, y1 direction, and these are all the other directions. Then you could ask, you see, there's certainly a volume-preserving embedding from this into the cylinder, because you can just squeeze in the first 2 directions and then expand to compensate the volume in the other direction. That's certainly true. But the question was, when is there a symplectic embed? And what Gromov showed was that there's a symplectic embedding only if this number A is actually less than that number A. So there's no way of taking a round ball and squeezing it symplectically to put it into a cylinder. That's that was his argument, and that was his result, which is a sort of complete contrast to this. So this is going to be true. I suppose we need to have n at least 2. So my dimension is 4 and above. So this is actually, you might think it's just a curiosity, because embedding, you know, this is not the kind of question one looks about in other kinds of mathematics. On the other hand, this is absolutely a fundamental result in symplectic geometry, because you can define an invariant. Suppose U is a subset of Euclidean space. You can define an invariant called the Gromov width of U or something, which is the maximum of A such that, the supremum of A such that the ball of size A embeds symplectically in U. So use a little open set and you look at how big a ball you can embed it. So you can certainly embed a ball of some size, and of course you take the maximum. And so this is a symplectic invariant of U. So if you move U by symplectic morphism, this won't change. And the claim is that, so this is a symplectic invariant, and the claim is that if phi is a diffeomorphism, with the property that it preserves capacity, so the capacity of phi U is equal to the capacity of U for all U, then that implies that phi, well, it's essentially a symplectic morphism. It preserves the symplectic form up to some. So I should make this orientation. Anyway, the point is that this notion of capacity, what you can put into a set, really characterizes what is symplectic morphism. So it's in some sense a complete invariant. So it's, it really is, this result is a crucial result from one way of looking at symplectic geometry. So of course, when this result was proven, then people started thinking about variants. And Gromov himself made invariants, different versions. He was looking at what would happen when you embedded two balls and that kind of stuff. So there was actually a lot of work. Potterovich and I did some work in the 90s about betting equal-sized balls. And things that this is one of the few results you can prove in arbitrary dimension. Most of the results you can prove are in dimension 4. There's somehow much better techniques in dimension 4. So the problems I want to talk to you today about, but perhaps before I go on, perhaps has anybody got a question? Was this okay?
You said there are topological invariants coming out of this. What did you mean? Topological invariants in what sense?
Well, I mean symplectic topology.
Symplectic topology.
Symplectic topological invariant. You see, this is like a symplectic topological invariant, right? And one of the things, why I say it's topological rather, I mean, there's the question of whether you talk about symplectic topology or symplectic geometry. One of the things is, it's, one of the consequences of this is that if you have Pn, which these are symplectic morphisms, and they converge C0 to phi, which is a diffeomorphism. So that means that in a uniform norm, so you forget about the convergence of derivatives, but just point-wise, they converge to this diffeomorphism. Then Pn being if these are symplectic morphisms, that implies that phi is a symplectic morphism. Because this capacity is a sort of topological invariant, so it was preserved by C0 limits. And so that means that symplectic geometry, in some sense, it's got a certain amount of rigidity. You can't take something which is symplectic and just move it a little bit. It will remain symplectic in this sense. So that's why people talk about symplectic topology and why people are interested in studying phenomena which are somehow robust and have some persistence, like this capacity is a very robust kind of invariant of a set. And other ones which might be more delicate. Anyway, so the question I was planning to tell you about today, actually I think that
it stopped altogether.
Completely given up.
Yes.
Right.
It's nearly 3:15.
Yeah, I've got to watch on. Okay, don't worry. Okay, so I was going to talk about embedding ellipsoids. So we have an ellipsoid, say E, A1, C, A, N is just going to be the set of numbers X where the sum of I, X, I, Y, I, A, I. So that's a general ellipsoid. In fact, I'm mostly going to talk about the case where you just have, I'm going to suppose these are ordered, and mostly just talk about the case where n is 2, so we're in 4 dimensions. So there's ellipsoids and there's polydiscs, which are another kind of shape you can have, which are just products of discs. And of course, there are many embedding questions you can ask. You can ask them, when does one ellipsoid embed in another? When does one polydisc embed in another? When do, etc., etc. When does one thing embed in another thing? And what we can say from Gromov's squeezing theorem is that if, if you have if E, A1, AN embeds into E1, EN, symplectically, then we have to have A1 less than equal to B1. That's from the capacity. Because you see, inside here, you see these sets get bigger if you increase A's. So we suddenly have the ball of size A certainly inside here. And if that embeds in there, this ball is inside here, and then the non-squeezing theorem tells you that A1 has to be less than B1, because this sits inside B1. So we know that. And then you obviously have a volume constraint, so that tells you that A1 times AN has got to be less than B1 times BN. And then the question was, Hofus was very interested in this and posed the question, are there any other general statements you can make of this kind? In particular, does there exist a function of A1 and 2 such that the existence of an embedding implies that FA1A2 has to be less than or equal to FB1B2? See, symplectic geometry is a two-dimensional geometry, and we have the capacity which is sort of picking out the lowest one there. And then the question is, and we have the volume picks out all of them, but I mean, there's any intermediate one, but the first one that would be obvious to look at would be something involving just the first two. And that was an open question for a long time until Guth showed no, that there isn't such an embedding. Rather to people's surprise, because people were looking for such a thing. But what he showed was that you could have an embedding of E1 and then R, well, all these are big, sitting inside E, well, he probably did it like 310, and then he had, well, I'm going to give you bad numbers, but it doesn't really matter what I give you here, something like that. He claimed that there exists an embedding for all R. And so the point here is that the R here is as big as you want, so your function F1R presumably would be growing with R, while here these are bounded, and so your function FA, this would be bounded. And therefore, the fact that such an embedding exists just shows that there isn't such a function. And that's done by a very clever explicit embedding. You just construct this embedding by twisting your ellipse around a torus somehow. I mean, it's a beautiful construction. Of course, it doesn't work. You have to have this one here. It doesn't work if you do that. So but there's a whole lot of questions about are there any other clever ideas, clever embeddings that give you a qualitatively different kind of thing? And, this is about all we know in higher dimensions, except for some new work of Kind and Dusa, which I won't have time to tell you about, but they have generalized some of the work in 4 dimensions, so they have some results in high dimensions. But their results, this is a completely new embedding technique. They're just very geometric and very beautiful. This one, what they do is they take things in 4 dimensions and they sort of incrementally push them into 6 dimensions and 5 dimensions. Very cleverly, I will say, but they don't have any new embedding technique. But what I wanted to tell you was what we can say about embedding in 4 dimensions, because in contrast to the question about embedding ellipsoids in higher dimensions, we completely know when one ellipsoid embeds in the other one into another one in dimension 4. Perhaps here I probably won't have much time to say anything about polydiscs, and what I should say is that that's a mystery, even in dimension 4. Polydiscs are they're sort of square objects, and they're complicated, and we don't know how to deal with them. So for ellipsoids, there's a theorem that tells you that EAB embeds in CD if and only if some numerical condition. I'll have to explain what this is. You've got a set of numbers here coming from AB, and you've got another set of numbers coming from CD, and these are meant to be pointwise different from each other. So this was a conjecture. Hofer corrected after his earlier conjectures were proven wrong, and I proved this a year or so ago. Now, what are these numbers? Well, NAD is the set of numbers you get by taking NA plus L being for M and M say integers. So you take that set of numbers with multiplicity, so you arrange them in increasing order with multiplicity. So, for example, N14, for example, is 0, because you're allowed zeros here. And then there's only one way of making 1 and 2 and 3, because you just have to take multiples of 1. But when you get up to 4, there are two ways of making it, because you can either take 1 times, you can take 4 times 1, or you can take 1 times 4. So you get 2 lots of 4. And then once you've got 2 lots of 4, there are 2 lots of 5, 2 lots of 6, 2 lots of 7, and then 3 lots of 8. And I will to go on. But you can imagine what that sequence is. And N22 is, well, you start off with 0, but now there are two ways of making 2. And then there are all even numbers, of course. There are 3 ways of making 4, because you can take twice that, some of this, or twice that one. And then there are 4 ways of making 6, and 5 ways of making 8. And so you see, from what I've written out, that this set of numbers is less than that set of numbers. So that's exactly at each place. So that's a comparison architecture. You look at one set of numbers, look at the other, and see where just compare them at each place. And then the claim is that because this set of numbers is less than that set of numbers, that's going to tell you that E14 embeds into E22. And actually, I've got to make these, to make this strictly correct, I've got to make these open a bit. Because if they're closed, the boundary won't quite manage to fit in. If they're open, that's the correct thing. So, this is a very numerical statement. And I think it's worth pointing out that the analogous things in higher dimensions is definitely wrong. So you can clearly do this if you have 3 things here, you can get the same set of numbers. But you see, Guth's examples, you can easily check and give you a counterexample. So, Guth's embeddings don't obey that. So this is something, it's just a 4-dimensional result. And I should point out, this is really, these sets of numbers have dynamical meaning, because as I told you, if you have an ellipsoid, it's got these 2 main orbits. One of them has got sort of, one of them, well, you see, if you have an orbit in a circle in Euclidean space, you can always bound it by a disk. And this A that's associated with this, you can think of as the area of that disk, because this is, the radius is r, but pi r squared is a symplectic area of that disk. And so that's what you call the action of this periodic orbit. And then we have this other periodic orbit, the other one size b, and it's got an action. And what these things are, they represent combinations of these periodic orbits. And actually there's a homology theory that you can build called embedded contact homology, where the sums of these periodic orbits, taken with multiplicities, form the chain. And so these are actually the energies of the chain of that homology theory. That's ECH, embedded contact homology. And there are actually before, I mean, this is a theory due to Hutchins and Taos, very much a 4-dimensional theory, now known to be equivalent to some kind of algorithm theory. So it's a gauge theory, it's a topology, you get topological invariants out of it. But you build it in this very geometric way from things on the surface, on the boundary of 4-dimensional manifold. And actually, using this embedded contact homology, you can prove half of this result. You can prove that if there is an embedding, then these numbers have to be, this set of numbers has to be less than that set of numbers. Because there's some kind of coordinate result with these are generators. Actually, I say they generate the homology. They are actually, the boundary operator happens to vanish in this case. So they are the homology. And then there's a cobordism map which increases energy, so actions increase. But this homology theory doesn't give you the other way around. It doesn't, yeah.
The same reasoning seems to work in higher dimensions, no?
But this theory doesn't exist in higher dimensions.
Oh.
There's something called contact homology that exists in higher dimensions, which gives you something called the Ekelund-Hofer capacities, which is a different set of numbers. See, the point is, this is embedded contact homology. So I don't know if what it does, the boundary operator is given by counting embedded homomorphic curves going from one orbit to another orbit. And that only has real meaning in dimension 4, because the homomorphic curves are two-dimensional things, and to say it's embedded has some meaning. If you're in 6 dimensions, say, well, everything's embedded. And anyway, this turns out to be a gauge theory. So you can't set up the theory. It's a 4-dimensional theory. You can't set it up in high dimensions, and it's wrong in high dimensions. And this set of numbers that you get, the Ekelund-Hofer capacities, what they are, they're sort of like this, except the capacity is EH of EAB. You just take the multiples. You just take M, A, and N, B with M and zero, and it arrays in the order. You don't take sums. So they're a much smaller set of numbers. And actually, Helmut's original conjecture was that it was the Ekelund-Hofer capacities that did everything in 4 dimensions. But in fact, you could actually, I mean, if people had just thought a little bit, they would have realized that didn't work. But they didn't think it the right way, so they didn't realize it didn't work very well. Yeah, so the fact that it's 4-dimensional is a bit subtle here. The methods that you use, you see, the other part of this proof is to show that if these numerical conditions are satisfied, then you have an embedding. And that's a very definitely 4-dimensional construction. And not an explicit construction. It's a much more indirect construction. See, this construction of growth is completely explicit. You could just tell people what to do. It would take a bit of time, but you could. So, let's see. I've got a bit of time. I thought I'd try and tell you a little bit of, I don't know how much time I have to tell you the proof of this, but one of the things is that these numbers, NAB, have a lot of interesting number theory associated with them. And you know, when I look, if you look at sets of numbers like this, I mean, you can actually write down formulas in this case, but usually they're just completely opaque. There's no way that one can really understand them. But after I realized that, I was talking about this with Michael Hutchins, and he made some, if you have C, which is a set of numbers, you know, it's C0, C1, C2, and so on. And you have B, which is another set of numbers of the same kind. Then there's a way of combining them that really he developed because he was trying to understand, in terms of embedded contact homology, what are the natural operations. And you know, if you have 2 3-manifolds, the natural thing to do, one natural thing to do is to take their union, right? Disjoint union, that's an obvious. So that has an analogy here. And what you do here is you say that the kth element of this is the supremum of Ck minus I plus di for I going from 0 up to k. So that's sort of a way of taking 2 of these things and combining them. And the amazing thing is that if you take something like NAB, that's equal to, well actually that's easy to write it this way, NAA plus B, where A is less than B, is equal to NAA, sort of connected, joined to NAB. So what you have to think of is this sort of corresponds to a ball, and this corresponds to an ellipsoid. And if you're used to doing these things, somehow when you're doing embedded contact homology, you're trying to work out the indexes, and you find lots of continued fractions coming up. And it's very interesting. And you can get at these numbers actually by counting lattice points in triangles. If you sort of in that mode of thinking, this is the kind of identity, it's related to the Euclidean algorithm, because you can think of reducing an A and a B, so if A is less than B, then you reduce it to A and B minus A. You know, you think of that this is sort of the trivial bit, you go on to this bit, then you reduce it to A, B minus 2A, and so on. Well, this is still bigger than that. You go on till you get A, B minus QA, KA, where this one now is less than A, and that's the remainder, and then you switch, right? This is now Q, and then you start with the pair QA, and you go on. So this is Euclidean algorithm. It's exactly the algorithm you use when you try and understand, one way of thinking of trying to understand the continued fraction expansion of a pair A over B. So you see if you take 8 over, well, you've got like 25 or something, 21, say. So then we can mark off some copies of 8. So that's an 8 and an 8. So we start off with 8, 21, and we take away one 8 and take away another 8, and then you're left with a 5. And then you put a square in there, and then you're left with 3 there, and you actually have 1, 3. This isn't a very good picture. Should look more like that. And then this is you've got left with 2 there, so you have a 2, and then you have a 1 and a 1. And what that picture tells you is, if you want that, it tells you that 21 over 8 is the same. We've got 2 of these. It's 2 plus 1 over 1 because you've got 1 of these, plus 1 over 1 because you've got 1 of these. Lots of 1s in this expansion. 1 over 1 plus 1 over 2. So it's the continued fraction 2, 1, 1, 1, 2.
So in that formula, do you need A less than B or B just positive? Because it seems like you do.
Well, I'm doing it with A less than B because I'm doing it. I mean, if it would be less than A, you just reverse it. Because I'm trying to take this is A and this is B. And so I want to take a rectangle and cut it up into squares. So then the way I'm organizing it is I'm assuming the height is less than the length. So I get at least 1 square. Okay.
Yeah, but in the formula you wrote A plus B is greater than A, right?
Oh. Right, well that's here because I want, yeah, you're probably right. I only need I don't really need anything in this formula. This formula's, you're right, this formula's always true. It's always be possible. You're right. Anyway, the point is that this is somehow taking, I mean, that this algorithm here is somehow saying that you can take this pair of numbers if you start with A and B, and you can decompose it into, so in the end, it will tell you for any pair of integers, for all A and B, there exist numbers W1 through Wn, so that N and B is formed by NW1, W1, joined with all these sort of square ones. And those W's would be exactly these sizes, these 8s and these 3s, and be exactly this decomposition. Because there's this picture of just doing the algorithm for you pictorially that I've written down here. So it's somehow telling you that the invariant for an ellipse is related to a combination of invariants for balls. And moreover, this combination I told you that this operation comes from taking disjoint union. So somehow the invariants for an ellipse come from a set of the numerical invariants with disjoint union of balls. And it happens that you can prove there's an embedding, so there's a result that tells you that an ellipsoid EAB, and I'm supposing here that these are integers, well actually, yeah, I'm supposing these are integers or rational or something. is that this embeds into a ball, definitely four-dimensional. So for all rational ABs, let me write this down a bit better. There exist numbers W1 to Wn, so that the ellipse embeds into the ball if and only if a disjoint union of balls embeds into it. And that's something you can prove completely geometrically. But these numbers, of course, are precisely the same numbers that come up in this continued fraction expansion. So that's how those are the. So perhaps I can explain how the arithmetic, at least how if you can embed the ellipse, you can embed the ball. So the other way around is more complicated. That involves the kind of techniques, it involves some analysis, it involves resolving singularities. It's a sort of more complicated thing. But I can at least show you what's the relation of this kind of picture to ellipses. I mean, it looks completely different, right? But the relation goes through, the way I understand it, goes through something called toric models. So in symplectic geometry, you have a rather flourishing field which looks at toric symplectic manifolds, which are 2n symplectic manifolds with a Tn action. Because people are always interested in group actions in symplectic geometry because of the relation to classical mechanics and the fact that you can reduce equations using symmetries, you know, if you have the fact that you have a sort of rotational symmetry means angular momentum is preserved, that kind of thing in classical mechanics led to a lot of interest in studying symplectic manifolds with torus actions on them. Now, I'm just talking about four-dimensional manifolds with T2 actions on, and in fact, so I'm thinking of C2 with the, or R4, if you like, with the obvious action of the torus, which is just S1 times S1, just rotating in each of the two planes in the obvious way. And, you know, there's what's called the moment map, which generates it, but in this particular case, you can really think of it as a change of coordinates. You can think of, instead of using the coordinates x1 to y2, you can use the coordinates r1 theta 1, r2 theta 2, polar coordinates. And then you can simply forget these. You can just quotient out by the torus action, and then sort of use the coordinates t1, which is r1 squared, and t2, which is r2 squared. And actually, this happens to be the moment map for the circle action because I told you a quadratic form would just give you a circle action. Something squared. Anyway, what that does, you see, so if you take the ball of size A and you quotient it out, just look at its quotient by this torus action. Then, you know, this ball is given by, well, r1 squared plus r2 squared less than A. And when you quotient out by the torus action and you use these coordinates t1 and t2, that goes to a sort of square triangle, like sitting in the plane, which is a t1, t2 plane, just saying that t1 plus t2 is less than A. And t1 and t2 are obviously positive. So you map onto, and if it's an open ball, you don't try to map onto that, you map onto the open. And this is what you call a moment image. It is actually the quotient of this ball by this torus action. And so that tells you that, you know, a ball somehow corresponds to a triangle. And if you think of it invariantly, you've actually, when you're writing it out this way, I've chosen particular coordinates here, right? I've chosen sort of I've chosen a particular splitting of R4 into C2. And I could have used different coordinates, like I could have, if you think of it, this is C1 and C2, I could have used C1 plus C2 and C2, something like that. I could have used a different basis, which would have been just as good. And that means that this image here is really only well defined up to the action of SL2Z. So this triangle here would be just as good. I could sort of shear it and make it look like this triangle. If this is A, and this is A, and this is 2A, that's just a sheared version, and that's just as good. So you really get this, you really say that a ball corresponds to this is what I think of as a standard triangle, because it's two sides of the same length. And it's related to the integer lattice, but it's well defined up to the action of SL2Z in translation. And the thing is, you see, that if you think of an ellipsoid, this is a ball, but if you think of an ellipsoid where you've got EAE, so this is this thing divided by A and that thing divided by B, well that of course gives you T1 over A plus T2 over B less than equal to 1. That's a triangle. It gives you a triangle looking like that. And so ellipsoids correspond to triangles where these sides are different in them. Well, balls correspond to triangles where things are sort of the same in them. And so here, what I was doing was cutting up a rectangle into squares. But that is essentially the same as cutting triangles up. You take a non-standard triangle. See, I could make exactly the same thing. This is a slightly complicated picture, but perhaps I should do an easier one. Let me do an easier one. Let's take. So you can actually see it. Let me use 3, 5, which is a very nice, easy one. And here I really will use some colored chalk. So you see, if we take this, we do a cut there, and then we do a cut here, and then we do a cut there. And that cuts it up into something of size 3, something of size 2, and 2 things of size 1. And what I claim is that if we take exactly the same size, but I take a triangle instead of a square. And what I'm really thinking of doing is removing this point and then shrinking that down to a point and that down to a point, but keeping all this internal structure in the same relative position. So what that means is that this point remains, that point remains there. This line now goes to there. So this square that we cut off here corresponds to a standard triangle. And then this line, see that point remains where it is. That's 2/3 the way up. So that goes 2/3 the way up. And then this line here, well, this has been moved down to there. That goes to there. And then what you notice is that this is another standard triangle, because this has got size 2 and that's got size 2. It's skewed a bit by it, but you can shear it and it'll be a standard triangle. And then you've got this green point here, and you've got this. Well, that point remains the same. That's at this height. It divides that in 2, and then you've got this thing. So here we've got another standard triangle, because that's got, these are sort of affine lengths. It's got affine length 1 and affine length 1. That's also got affine length 1 and affine length 1. So that's 2 standard triangles. So the claim is that this decomposition into squares is completely analogous to a decomposition of this into standard triangles. But then that corresponds to, if you pull it back by this quotient map, which is called the momentum map, you see your triangle here gives you an ellipse, and each of these things gives you a ball. So what you've done is taken the ellipse, which was in this particular case was EC prime, and what I've done is I've written it as the size of a ball of size 3, union a ball of size 2, union 2 balls of size 1. So that's telling you if you can embed the ellipse, you can embed the balls, because you can simply cut the ellipse up into balls. I'm slightly fudging something, but you probably won't notice. But then there's a complicated thing, how do you put it together again? If you have the balls, the claim is, you can embed the ellipse. And you certainly just can't take the balls and stick them together. At least I certainly can't. There's somebody hoping to do something similar, but I don't think you can. Because you need, if you're going to stick them together, you need some skeleton to stick them on. And that skeleton to stick them on involves some complex geometry and stuff. So I think this is a good place to stop, and I'll stop here. Thank you.
Question?
So is there any conjecture on, these kind of theorems in higher dimensions? Do you state something?
Well, that's what I was telling you about.
Yeah.
This result is definitely wrong.
Yeah. No, yeah, but
and nobody knows what the right answer is. We don't have a conjecture.
Oh, yeah.
There's the Aiken-Hofer capacities. I don't know quite how good they are. I don't think that anybody thinks that they're a complete invariant. And there's ghost embeddings. And then there are some clever results of Dusa and Heim that take this result. I mean, you can take, if you have an embedding in 4 dimensions, you can somehow up the dimension by thinking of 6 dimensions as 5 over 4 dimensions. And so that gives you, if you know that some embeddings exist in 4 dimensions, you can then construct from them certain embeddings in 6 dimensions. But that's certainly not the complete story. And so I don't know what the right answer is.
So there was this question of Hofer, but was answered negatively by Guth, right?
Right.
And what if you change this question, instead of f and g of a1 and 2, you say a1, a2, a3?
Oh, well, it's the same.
Same.
I mean, it goes to examples extent to give kind of examples of that. I just told you the first one. So the result there is there are no intermediate things. But yeah, I mean, I think it's just an open. This is all fairly recent. So it was, I don't know when it was, 3 or 4 years ago. So there hasn't been any other similar idea.
And for polydiscs, there is nothing.
Well, for polydiscs, people, you see, polydiscs are sort of awkward, and what people think is that if you have a polydisc, which is a sort of square thing, you can ask if you take the polydisc 1, 2, which ball does it embed in? So if you want the infimum here, the smallest ball will take P1, 2. If you take P1, 2 plus epsilon, then you know that that embeds in something a bit less than P3 plus epsilon. It embeds in 3 plus, less than epsilon. You see, the point is that, perhaps I should stop. The ball VA, you think of as a square, as a triangle. The polydisc is obviously like a rectangle, right? Because it's just a product of something, so it looks sort of like that. So if you have a polydisc with size 1 there and size A there, then P1A obviously embeds into P1 plus just linear, just pretty tip. And then the question is, when can you do better than that and when can you do worse than that? And you know that if A is bigger than 2, there's a folding procedure where you can actually do slightly better. But nobody knows quite how much better, but you can do slightly better. But at A equals 2, the folding doesn't work anymore, and the suggestion is you can't do better. So that the infimum here, the suggestion is that that's 3. But that's not proven. Because you don't have a nice round boundary. You don't have, you can use similar kinds of invariants. You can use these embedded contact homology invariants, actually, by smoothing the boundary and looking at the characteristic flow on the boundary and seeing what you see. And they don't quite give you what you want. They give you some obstructions, but not as good as this. So they're not good enough. And so the question is really, how much does this flow on the boundary, how much information, that's a sort of topological information does it have? I mean, that really is a sort of topological question about the sort of dynamics and flow. Well, you can approximate this rather quickly. So Hutchins has done some pretty good calculations, and if you just round this corner a little bit more and more, what you get for what the sort of limit of the embedded contact homology is. It's not a good enough invariant. Well, of course, there are other invariants which are more using J-homomorphic curves and things, but they haven't quite managed
So again, there's dinner, and if you are interested, just, you know, the usual, make yourself known to Andre, and after this.